Hello everyone, today we are going to talk about computer networks. I guess you also agree with me that internet is amazing. With just a few clicks, we can send messages, we can play computer games, we can stream video, etc., etc. This ability of computers to send and receive information over a global telecommunication network changed the world forever. Because if we look a bit back, we see that in about 150 years ago, just sending a mail from London to California with an express mail would take up to 2 or 3 weeks. But now we can just send emails in a fraction of a second. This is a huge difference, of course. So let's go back in the history of computers. Were computers and networks always hand in hand? Did we have computer networks since the beginning of appearance of computers? The answer is that no. So before 1970s, most computers worked alone. You remember from the history of computers that the initial computers were too large, they were very slow, very bulky, and they were very limited in terms of their functionalities. They could themselves barely do simple stuff. They were not connectable at all. And their number was so few in the whole world. So they were not taught at the time to be connected to each other. But later on, as desktop computers are starting to show up on people's desks, then it became useful to connect them together. And the reason for that would be to share data, for example, or share resources. And now let's just briefly see what a computer network means. A computer network is a set of devices, or they're also called nodes, that are connected together through some links. A node has the capability of sending and receiving data. And it can be, for example, a computer, a router that you have, for example, one of it at your home that connects you to your internet provider company. And it can be also hardware devices, for example, printers, etc., or mobile phones, anything that is in some way connected to the network and is capable of sending and receiving data. And the link is a medium that connects the nodes together. It is also known as communication channel. So nowadays we have different sorts of links. For example, we can have copper wires. We can use even air for our communications. In Wi-Fi, you see that it is done through the waves that are sent into the air. And also optical fiber cable is another instance of a link. The first networks appeared in 1950s and 1960s. And the original networks were usually small and were just inside an organization. And the organization would benefit from those networks to facilitate the exchange of information between people and computers. Because before emergence of computer networks, sharing data would be done, for example, by physically moving memories, for example, moving piles of punch cards or reels of magnetic tapes that contain the data. And you see, obviously, this is not easy at all. And if it happens that, for example, your punch cards fall on the floor, then you have to collect all of them. You might need to sort them in the correct order. This was not easy at all. And networks would be even useful to share as physical resources such as printers or large storage devices, because the storage in the beginning was very expensive, and the memories inside computers was too limited. So they would benefit very much if they could connect through some network to a larger storage. These small networks inside organizations were called local area networks, or LAN. We are even using this term nowadays for small networks, the very primary networks, for example, inside our homes that consists of our TV, for example, our computers and mobile phones that are just connected to the network in our home, or our LAN. So examples of LAN can be simply 2 computers in a room, or it can be bigger, for example, computers of a university campus, which can have like hundreds or even thousands of computers. Now let's review quickly what technology is used to connect the computers inside the LAN, or connect the nodes, I should say, inside the LAN. So Ethernet was the traditional technology for connecting devices inside the LAN. And it was developed in 1970s. You can see here in this picture an original sketch of Ethernet from that its inventor drew. And it became the most famous and successful technology for LANs, and it is even used today. So what it does is to enable the computers to communicate with each other via a protocol. Protocol is simply the language that makes the computers communicate with each other inside the network. So earlier in the programming lecture, we saw that we humans interact with computers in terms of programming languages, and we give them instructions and so on. When computers want to talk to each other inside the network, they have other languages, which are called protocols, which are sets of rules that using them, the computers can send and receive messages to each other. And we, in these lectures about networking, we're going to talk a lot about protocols. We will see different protocols at different levels of abstraction, like we had programming languages at different levels of abstraction. So here you see a picture of Ethernet LAN, which are even used today. I'm sure you have some of these at your home to connect to your router that connects your LAN to your internet service provider.
Now let's see step by step how data is transmitted in Ethernet. Imagine this is a LAN that is consisted of 6 computers that are connected to each other with Ethernet cables. Then they can communicate with each other by writing to these cables. And writing is, which means like sending information, is done by sending signals into these wires. We are not going to go to the details of how data, which is in terms of bits and zeros and ones, is transferred into signals, but this is out of the details, but this will be done, and that data and those signals will be sent on these wires. And the computer that does this operation is called the sender, who sends the data. And then when it sends those signals on these wires, these wires, they are received by all the computers that are connected to this LAN. But of course, this computer intends to send the data to some specific computer or to some specific node here in the LAN. But how should they know to which one the data is being sent? In order to determine the receiver of each message, Ethernet requires that nodes that are connected to a network have unique addresses. These addresses are called MAC addresses. MAC stands for Media Access Control, and it is a protocol, a set of rules that are used by computers that are connected to a LAN to communicate to each other. So every device that can be connected to internet is given a unique MAC address, which is set by the manufacturing company. It is unique in the whole world, so you will not find two nodes that can be connected to internet and have the same MAC address. Then this MAC address is used in this way. So whenever a node wants to send a message to another node in the network, it will put the MAC address of the receiver in the beginning of the message. So this MAC address will precede the message. So imagine, for example, now here A, B, C, D, E, F are the MAC addresses of the nodes in this LAN. And A wants to send the message to E, so it will put E, which is the MAC address of this node, in the beginning of its message. And the computers that are connected to a LAN listen to the network, which intuitively means that they check the carrier, they check the transmission medium they are connected to. So in case of Ethernet, they check their this Ethernet cables, or if they are connected through Wi-Fi, they check the signal sent in the air. And if they receive some, if they detect some data is being sent, then they only process that when they see that their address, their MAC address is in the beginning of the message. So they only pick that messages that belong to them. And every computer nowadays has two MAC addresses, one which is used for Ethernet and the other one which is used for Wi-Fi. So now let's see in what way the computers that have now a unique MAC address will send data. For this purpose, they use a protocol, which, as I said, is a set of rules that allows the computer to communicate with each other. They use a protocol called Carrier Sense Multiple Access, or CSMA for short, to send data. And this protocol requires that each node that is connected to the LAN verifies the absence of other traffic before transmitting media. It simply means that all the nodes that are connected to the LAN will check the carrier or transmission medium here to see whether or not there are other signals on it. If there is other signals on it, it means that another computer is sending data. But if they see that no one is sending, then they can send their own data. So we have the notion of carrier here, which is simply any shared transmission medium. In case of Ethernet, it is copper wires, and in case of Wi-Fi, it's the air that carries radio waves. So computers all at the same time sense this carrier and access it if it is empty. And if it is not empty, they have to wait until it is empty, and then they send data. And the bandwidth is the rate at which a carrier can transmit data. So what might happen is that we might have collisions. Imagine, for example, node A and node F. Here first sends the carrier and see that no one is sending and the carrier is free. So they start sending both at the same time. So then when their signals reach together, they will collide, and then this their data is not useful anymore. Imagine you throw two stones to a lake, they will create some waves, and then when they get transmitted, and then when they reach to each other, they will be mixed up together. So you cannot recognize any of the waves after that. So it's the same situation. The data which is sent by A and which is sent by F will be ruined after the collision. And the computers can check that the collision has appeared by checking the wire. They check the signal that is present on the wire and will see that it is different, for example, from the message that they had sent. So they realize that it is that a collision has appeared. The solution for this would be to stop transmitting when a collision happens and wait for silence, and then try again. But the problem is that if you stop and then start sending again, other computers might also do the same thing. So the collision will appear again and again and again. So a fix for this, which was introduced, was that first, the computers wait for a small and random time before retransmission. So then the time that, for example, A will wait will be different from the time that F will wait because they pick random times. And then each time a collision appears, they will back off. And this back off will increase exponentially, meaning that, for example, if the first time after a collision they wait 1 second, the next time they will wait 2 seconds, and the next time 4 seconds, and so on and so forth. This is to make sure that the rate of likelihood of collision will be reduced. And many transmission protocols use this way of detecting and resolving collisions. For example, both Ethernet and Wi-Fi use that. But this solution is yet not enough. The problem is that when you have a large LAN, no matter if you back off exponentially and the computers wait for a random amount of time, etc., because they are too many, the likelihood of collisions is too high. So lots of time will be lost by just collisions and resolving from collision and so on and so forth. So another solution is to shrink the number of devices that are using the same carrier or which is shared between them. This shared carrier is called also the collision domain. It is a domain in which the collision might appear. For example, it can be the Ethernet cable. So the solution would be to break the network to smaller collision domains. So we see here in this picture, imagine in our original schema, we had 6 nodes being connected to this LAN by Ethernet cables. This is called one collision domain because all of them are sharing this Ethernet cable. But as a solution, we can break up this network to 2 collision domains, and then we connect them using a device which is called the switch. The role of a switch is that it separates, it's kind of like a door between these collision domains, and it helps in reducing the number of collisions. Let's see how a switch works. So it sits between 2 smaller networks and only passes data if necessary. For example, if A wants to send some data to C, then here it doesn't need to go through the switch. So the other nodes at the other end of the switch will not see that data, and they can communicate with each other, and the rate of collisions will be much less than the previous case. But if A wants to send some data to the other part, for example, to F, then the switch will actually let its message pass. And for doing this, the switch needs to have a list of the MAC addresses on both sides of the network. For example, it knows that these 3 nodes with their special MAC addresses are at this part of the network, and these three other nodes are on the other part. And when it sees that a message has a MAC address that belongs to A, then it sends that message on the wire in this collision domain. In this collision domain. So this principle is used also in bigger networks, for example, the whole internet. So it means that we have connectors like switches all over the internet, but they are more powerful. They are usually called routers. That their role is to interconnect a bunch of smaller networks. So here you see, for example, we have two smaller networks that are connected to each other using a switch. The same principle is used for connecting other bigger networks as well, which allows inter-network communication without collision. So imagine you have several smaller networks being connected together. Now you have a bigger network, and now there can be several passes inside this network to send the same message from a sender to a receiver. For example, imagine this computer wants to send some data to some computer here. It can, for example, go through this path, or it can go through the other path. The bigger your network becomes, the more passes you have. So the question is how to decide the best route. For this purpose, switching techniques were introduced. There are typically three main switching techniques, which are called circuit switching, message switching, and packet switching. So circuit switching means that is very simple. It means that whenever you want to connect to a network, dedicate some special medium or some special line to them, which is dedicated to them, and no one else will use it. It is private to them. So it is like the old phones which were used. So each one, a person wanted to call another person, it had to ask some operators to dedicate to it a private line. So they switched the circuit to the for the needs of their the parties involved in the communication. This is the problem with circuit switching, is that it is inflexible. Each time you need to sort of change your circuit which you are using. And it is expensive, because if you want to have a private line, it requires a lot of resources, and it is expensive, and it's not affordable for many users. And what will happen is that this line is normally not used in many times. So you will basically waste a lot of the capacity of your network. For example, if you had a private telephone line between you and your friend, so in most of the times during a date, you would not use this line. So it will waste all the resources that are used to it. So circuit switching has its own benefits. It's that it is exclusive to you, and it brings you some sort of privacy and safety, but it is only used in special cases that need a lot of privacy and very high speed communication. For example, it is used in military and maybe some banks and high importance operations. And so for their purpose, they will dedicate some circuits to connect their nodes that they have. For example, the data centers in a military or a bank, etc. So they will not basically share their network with any other one. It is exclusive to them. Another switching way is called message switching. In message switching, we will have an approach which is similar to postal system. So in postal system, we have several nodes that will receive messages and forward them. For example, here we have a postal package which we want to send from here to here. Then there are several terminals on the way which will forward our packet until it arrives to its destination. And several passes are possible. So it's not just a single circuit. There are several possibilities. So at each stop, it is clear where to send the packet next, the message or the parcel, where to send it next. And the different routes are possible. The benefits is that it's more reliable. For example, imagine some of the terminals happen to have some sort of problem, then the message can go through another way. This same principle is used in routing. So if some switches or routers happen to have some problem, then the whole network will not go down. Other passes will be tried until the message hopefully is sent to its destination. So we have a level of fault tolerance, meaning that if there are some faults, we can tolerate it and we can still have the operations of the network. So in this way that we are sending the messages from to different locations until it reaches its destination, we will have a number of devices on the way, which are usually routers in case of networking, that take our message and pass it through its route. And the number of the stops or hops a message is going through, it's stored in the message and is updated each time it reaches a new stop. This number is actually very important because if we keep track of it, we can identify if there are problems. For example, maybe in our routing in the previous picture, we happen to have a loop. For example, the message is forwarded here, then it is forwarded here, and then it is sent back here, and it goes on and on in this loop. Then each time that we know that each time the hop count, which is the number of stops that has passed so far, it is updated and it's incremented by 1. So when we see that this number is getting too large, we realize that there should be a problem. So we can think of a solution for that. And for example, one solution is to set a limit for the number of hop count, which is called the hop limit. So maybe, for example, an easy solution is to drop the messages that go beyond some hop limit. At least this will allow other messages to use the network and they will not occupy the resources. But there are the more smarter ways to solve this as well. So message switching has also some drawbacks. For example, the first one is that messages might be too big. So when the message is then sent along the network, it will need that very tiny messages just wait for a long time until this big message is forwarded through the network. The solution is to chop up big messages into small pieces. In the networking terms, they are called packets. So a message is chopped up to several, maybe many small packets. And then we introduce packet switching. Packet switching is a routing approach, means that it's a way to let our data be transmitted from the source to its destination. And as I said, it chops up data to smaller packets. And it's like the previous time, it has several different routes. But the difference is that here we don't send the big message as it was originally. We break it down to several smaller packets and then send them. And then these packets are independent of each other. They can be sent through different passes. And then when they are received by the receiver, they might arrive at a different order, which can be solved then later. The benefits of it is that it is efficient. For example, you will not clog up all the network for sending big messages anymore because everything is divided to smaller packets. And we are still fault tolerant because you see it's like previous time, we can have our different possibilities in routing. And it's decentralized, meaning that we don't have any central authority to control this sending. Each router on the way will decide on its own where should be this packet forwarded to. The whole internet actually runs on packet switching. So a packet is basically a piece of data plus some destination address, which gives it an address on the network. And how these addresses will be specified is again defined by another protocol on its own. It is called Internet Protocol or IP. I guess you have heard the name IP and you have seen many instances of IP addresses. For example, maybe IP address of your laptop or your mobile phone. So it's this IP is a standard which was created in 1970s and it is still used today. So today's IT number version 4 is used, and the IP version 6 is the next version that might be used in future if IP version 4 is not enough anymore. So let's review what is a network protocol. So a network protocol like IP, for example, or other ones that we have seen so far in this lecture is a set of rules that determine how data is transmitted between different devices in the network. It determines basically how different devices, different nodes in the network communicate with each other. For example, IP here tells us how to give addresses to different computers in the network. They are different from MAC addresses. MAC address is an address which is unique worldwide and is set by the manufacturing company. But IP is a sort of logical address. It is not bound to your machine. It will change from time to time that you connect to internet. So every computer that wants to get connected to a network needs to get an IP address. As I said, it can be different each time that a computer connects. For some specific computers or nodes or devices, it is fixed. It is called the static. For example, like routers, etc., have their own IP. Which never changes. But for other devices, for example, our laptops or mobile devices that are sometimes connected and sometimes not connected, they will get different IPs each time. And an IP address consists of 4 8-bit numbers, which are separated with dots. For example, this address that you see here is the IP address of one of the Google servers. So you see it says 172.217.7.238. Each of these numbers consists of 8 bits. We have seen that with 8 bits, we can show from 0 up to the power of 8 minus 1, which will be from 0 to 255. And a router, as I have said its name several times in this lecture, is a device that connects 2 or more packet switch networks. Packet switching is the mechanism that is used primarily in internet today. Circuit switching and message switching are not used universally. They might be used for some specific purposes of some companies, organizations, etc., but they are not used universally. They are too expensive to be used for the whole world. So routers forward data packets to their intended IP addresses, meaning that whenever they receive a packet, they see what is the destination IP address, and then based on that, they forward it in the right direction. So for example, here we have a router here, which connects these networks to outside, and upon receiving messages, it will decide which way it has to send it. And besides sending messages, routers try to balance the load across the routes they know, because a router might be connected to several different routes, and maybe so we saw that for a message, maybe several different routes might be possible for it to get to its destination. So routers take care of the load on these routes and try to balance it so that, for example, one route is not left empty while there are others which are too occupied and have long waiting times. And the routers ensure speedy and reliable delivery by, for example, balancing their load and other mechanisms that they take care of. So nowadays there are routers all over the globe, and they work to each other. So routers have their own specific protocols to talk to each other. For example, they have protocols like Border Gateway Protocol or BGP or Internet Control Message Protocol to communicate with each other. For example, they learn from each other what are the addresses that they can send data to, and what the different routes exist in the network, and what line is congested, and what line is still free, and on which line the load is too much, etc., etc. So now we want to talk about TCP/IP. Very briefly, we will talk about this protocol in more detail in the next lecture. So we saw that packets of a message can take different routes because packets move independent of each other and go maybe in different routes through the network, but all of them end up, hopefully, they end up in the receiver, in the destination. But because they take different routes, they might get to the destination in a different order that they were sent originally. Imagine you have a text, a very long text, you chop it up to smaller text and send them by mail to its destination. Then because they might take different passes in the postal system, they might arrive in different order. And imagine there is someone sitting at the destination address and reading these mails that are arrived one by one. Then they will notice that they are not in the right order. So some applications will not tolerate this. For example, imagine you are watching a movie and you will not like to see that movie scenes are coming or shown up to you in the wrong order. So there are protocols on top of IP which handle this. One of these is called the TCP/IP protocol. As I said, we will talk about it in more detail in the next lecture. So such protocols will fix the order of the received messages. So now let's talk about ARPANET. ARPANET was the world's first packet switched network, and it is actually the ancestor to the modern internet. And it was a small internet initially, but it grew and grew and got bigger until 1977. It actually became internet. And it was originally named ARPANET because It was named after the US agency that funded it, which was Advanced Research Projects Agency. So here you see a drawing of the ARPANET, which shows how it looked in 1974. This is very interesting. You see here, this is the ARPANET, which is the internet of the time in the whole world. So you see barely 100 devices are connected to each other using this network. It was too small. It is listing computers in very different locations. For example, these small circles show different locations. For example, here we have some computers which are in London, and we have some other computers in Hawaii, Stanford, etc. So they are all computers that at the time were connected to each other and formed the internet of the time. But this network was too small compared to the today's internet, which is connecting like billions of devices to each other. It's not only computers. Nowadays, we have the notion of Internet of Things, meaning that basically devices are getting smarter. Many of the household devices even are nowadays connected to internet, and they can be checked, they can be controlled remotely, and this gives us a lot of possibilities. Compare it with this tiny network that could fit in a piece of paper. Nowadays, it is impossible to draw the whole internet on a piece of paper. So now that we have discussed a little bit about computer networks, I would like to talk about the OSI model. The OSI model, or Open Systems Interconnection, is a model which is a conceptual framework which is used to describe the networking system, how it works and how it is divided to different levels of abstraction. So it actually divides the networking to 7 different levels of abstraction. So you see here, it starts from the bottom with physical layer, then comes data link layer, network layer, transport layer, session layer, presentation layer, application layer. So when we work with computers and want to send data, for example, like send emails, etc., we send our emails at this application level. So we are far from all the details that are happening here. It's like, in some way, it's like programming languages. In high-level languages, we forget about all the details of the architecture of computers and so on. We just have high-level instructions to use. This is somehow the same concept here. So let's briefly see what these layers are. We have already discussed about some of them in this lecture. Let's see which they were. So we have already discussed about the layer 1 very briefly. So this is called the physical layer. It actually is concerned, this layer is concerned about the connections between the devices. The connections nowadays can be in form of copper wires, optical fibers, or radio links. And this layer talks about the fact that how data is which is in terms of bits, is transmitted into waves and signals, and how it is sent on the very low level connection devices. So in the next level, we go up in the level of abstraction, and this level, which is called the data link layer. In the data link layer, what we are concerned about is the node to the node delivery of the messages. It is what we talked about when we talked about LANs and MAC addresses and collision detection, etc. So in that part, we talk about node-to-node delivery of messages. What should we do to for example, how should we send the data? What should we do if a collision appears? In the physical level, for example, they don't care about collision. They just care about sending the data in terms of waves and signals. So the reason why we have these different levels in networking is that the work in each of them is very dedicated to a specific details that are hidden from the other layers in this model. For example, when a programmer wants to send a program that sends emails, it doesn't need at all to know about the details of sending signals and waves here or setting the correct MAC address and so on. So all these details are hidden from them and they just work at a high level. Or for example, when two computers are getting connected to each other by Ethernet cable, we don't need to care about how an email would be sent and how it is translated in terms of zeros and ones, etc. We just care about how to detect collision. And so each of these layers have their own experts that work with them, try to improve them. So the work is very specialized. So all these layers are getting better and better every day. Their own experts are working on them, making them more efficient, more reliable, etc. In the third layer, we have the network layer, in which so layer 3 is responsible for transmission of data from one host to another host, which is located maybe in a different network. In the data link layer, you have two nodes that are in the same network, for example, two devices in your LAN. But in network layer, you might be you might be sending something to someone in a whole different LAN. So it's it's a different network basically. So here we have the notion of routing that comes into the picture and finding the best route, and what if the packet doesn't arrive at the destination, what if it gets lost, for example, and how to address them. And this is where IP addresses were used. At level 2, MAC addresses were used. At level 3, IP addresses are used, which are logical addresses, as I said before. They can be changed each time you connect to internet. So this was for today. We will continue in the next lecture with level 3, with layer 3, and continue upwards in the network layers. And thank you for your attention, and I would like to encourage you to ask your questions from us via emailing us through Studium, or using the forum on Studium, or joining the drop-in Zoom sessions. Thank you again for your attention.